In section 7.1, we're going to learn to use the Pythagorean Theorem to find the sides of a right triangle. So in order to use the Pythagorean Theorem, you have to already know the length of two of the sides of the right triangle, and it will help you to find the third missing side. So remember that a right triangle has what are called two legs and a hypotenuse. Those are just special names for the sides of a right triangle. In semester 1, when we were talking about how to prove that triangles were congruent, we learned a theorem called HL. H stood for hypotenuse and L stood for the legs. So this is kind of something that hopefully you remember from semester 1, how to identify the sides of a right triangle. So to identify the sides, the hypotenuse is always what's called across from or opposite the right angle. So if you put your pencil on the right angle and just go away from it, you would be pointing at the hypotenuse. To identify the legs, you could do what's called trace the L in the picture, or trace the two sides that are actually meeting at the right angle, and you would be identifying the legs. So very important that you know where the hypotenuse is versus where the legs are so that you set up the equation correctly. Because the equation wants you to set the hypotenuse squared equal to leg squared plus leg squared. So notice how all the numbers are squared and the hypotenuse squared never has anything added to it. It's always alone. Now, if you have already heard of the Pythagorean theorem, they often say it's a squared plus b squared equals c squared, or c squared equals a squared plus b squared. I mean, that's fine, but I don't think that's very descriptive. I rather think of it as hypotenuse squared equals leg squared plus leg squared. Because when you just say a, b, and c, it's not really super clear what you mean by that. But what it does mean is a and b would be considered your legs and c would be considered your hypotenuse. So in example 3, we're going to find the missing side of a right triangle. So if you notice, if you study example A, B, C, and D, you can see on all of them only one of the sides is missing. So this is the way the Pythagorean theorem works. If only one of the three sides is missing of a right triangle, you can use the Pythagorean theorem to get the third missing side. So if we look at example 3, again, it's very important to differentiate the hypotenuse from the legs. So the hypotenuse is opposite the 90-degree angle. So 6 is my hypotenuse. My legs are the two sides that are making the L or meeting at the right angle. So if I set up the Pythagorean theorem correctly, in example 1a, I would be taking x squared plus 3 squared, and I would be setting that equal to 6 squared. I would be squaring my two legs, adding them together, and setting that equal to the hypotenuse squared. Again, very important that the legs get added up, but the hypotenuse stays alone. So 6 squared should stay alone. When you have an equation like this, always take the numbers and square them first. So x squared plus 3 squared is 9 equals 6 squared, which is 36. Algebra is all about isolating the variables, so subtract 9 from both sides. We end up getting x squared equals 27. And we talked about this on day 1. We're going to square root both sides so that our x ends up getting unsquared. And we should rewrite 27 as the square root of 9, the square root of 3, because 27 could be rewritten as the square root of 9, square root of 3. And the reason we do that is because 9 is a perfect square, so it's going to come out as a 3. So if you don't remember what I'm talking about, you'll have to reference lesson 7.0. So the correct way to answer this, or to solve this, would be to say that x is equal to 3 root 3. Now you could just convert that to a decimal. Like you could go to your calculator, take the square root of 27, and convert that to a decimal. But the directions tell you to state your answer in simplest radical form. So that would be going against what the directions want. The directions want you to state it with still having a radical in it. So you should not be converting to a decimal. All right, in example B, same thing. We know 2 out of the 3 sides, so let's identify the legs and let's identify the hypotenuse. Hypotenuse is across from the 90, so my x is my hypotenuse. My legs are the other two sides that are making the 90-degree angle, making the L in the picture. So the correct way to use the Pythagorean theorem would be to take the x squared, set it equal to 6 squared plus 3 squared. Again, notice I'm keeping the hypotenuse by itself, and I am also, of course, squaring everything, and I'm adding the legs together. So x squared equals, square your 6, you get 36. Square your 3, you get 9. Add up your two numbers, x squared equals 45. We always want to unsquare the x, so we square root it. Remember, these two operations cancel each other, so we end up with just x. But it's never, ever okay to just do an operation to one side of an equal sign. You got to do the same operation to the other side. So we would square root the x squared. We would also square root the 45. But you, again, can rewrite the square root of 45 as the square root of 9, square root of 5. The 9 will come out as a 3. So we end up with 3 square roots of 5 as our final answer. All right, let's try that one more time. In example C, we know 2 of the 3 sides, so we can use the Pythagorean theorem. Across from the 90 is our hypotenuse, and our legs are the sides making the L, or meeting at the right angle in the picture. So if we use the Pythagorean theorem correctly, we will take the two legs, x squared, 3 squared, square them, add them up, and set them equal to hypotenuse squared. Again, the Pythagorean theorem is leg squared plus leg squared equals hypotenuse squared. So where I have the highlights, those are the two things that should be squared and added. Where I'm pointing away from the red arrow, that should be squared but left alone. So we end up with x squared plus 9 equals 25. We subtract 9 from both sides. We end up with x squared equals 16. If you square root both sides, because you must do the same thing on both sides of an equation, we get x equals 4. So this one ended up as a nice perfect square, so it came out of the radical as a 4. All right, so it's the same thing in option D, but hopefully you're noticing on one of the sides that you have a square root. That doesn't change the fact that you still need to use the Pythagorean theorem because you know two sides and you don't know the third. So remember again how the Pythagorean theorem works. You know the hypotenuse is x. If you highlight the L in the picture, you know your legs are 10, square root of 10 and 7. You have to square everything. So if you set up the equation correctly, it's the square root of 10 squared plus 7 squared equals x squared. Just because there is a square root on one of the sides, don't let that throw you off. The Pythagorean theorem says hypotenuse squared is equal to leg squared plus leg squared. So go ahead and apply the Pythagorean theorem, and then let's work the algebra from here. So we learn in 7.0 that anytime you have a square root and a square right next to each other, they cancel each other. So the square root of 10 squared is just 10. 7 squared is 49, and we'll set that equal to x squared. If you add up your two numbers, we get 59 equals x squared. If we square root both sides so that we can unsquare that x, we simply get that x is the square root of 59. I can try to simplify this, but there are no perfect squares that go into a 59, so we would actually be done. We would leave that completely under the square root. So you should be noticing from these 4 examples that sometimes you can simplify the square root and turn it into something that has a number outside a square root and something inside, like happened in example A and B. Your number under your square root could be what's called a perfect square, like in example C, so the number comes completely out. Or like in example D, there's nothing you could do to simplify it, so the entire answer is left under the square root. So any one of those options is correct. And as I'm looking back at my work here, I'm noticing that I forgot all of my units. A good rule of thumb is if the original problem had units, you should have units on your answer. So in 3A, I should have had miles. 3B, I should have also had miles. In 3C, I should have had meters. In D, I should have had kilometers. So I apologize for that. I should have included units on my answer. Now, in my class, I don't take off if you don't have units unless it's a word problem. If it's a word problem, I'm going to take off points. So if we come down to the next example, you're going to see I am going to talk about word problems. So in these, it's definitely a case where I would want you to include units on your answer. I always want units on my word problems. All right, so if we look down below at example 4, we're going to see we don't have a picture of a triangle, right? We just have some words. Of course, that's what makes them word problems. And so we're going to start by talking about, well, if all they're going to give me is words, I'm going to have to draw a triangle and I'm going to have to label it. So when they tell me these words, where should I put the label? So some typical words that you're going to see in your word problems. First of all, you are going to have a right triangle. So let's put a box in the corner here. But some typical words you're going to see are, you might see the word height. If you see the word height, you should put that on your vertical leg. Remember, vertical means that the leg is going up and down on the page. If you see the word altitude, you should put that on your vertical leg. If you see the word vertical distance, which we might not see a lot in this section, but we're going to see it later in the chapter, that should be on your vertical leg. If we go back up to the word height, sometimes they just say something is 6 feet tall. That's another way of referencing a height. That should be on your vertical leg. All right, let's move over to the horizontal leg. If we look at this horizontal leg here, what are some words that let you know you're dealing with the horizontal leg? Well, one of them is horizontal distance. Another one is, very common, is to say the distance from the base. So if you're the distance from the base of a building or the base of a tree, it means the bottom of the tree. So you would be down there at that horizontal leg. I should have talked about this when we did the vertical leg. I should have talked about if you travel travel directions. So if you're traveling east and west, that is your horizontal leg. So if we go back up to the vertical leg, if you're traveling north-south, that is your vertical leg. Sorry, I think I said east-west was vertical. East-west is horizontal, north-south is vertical. We're going to do an example problem there, and we'll talk about that. And then the last thing, I got to squeeze this in here, so let me make a little room. The last thing we should talk about is anytime they talk about a shadow, shadows are on the ground. So shadows are something that would be horizontal. All right, and then finally, our hypotenuse. What kind of words would we see that let us know we should be labeling our hypotenuse? If they ever talk about the length of something like a cable, a wire, a string, a ladder, I'm sure there's more, but those are the typical ones. I'm going to write ... because there could be more. Those things should be your hypotenuse. If they ever just use the word distance, they don't say vertical distance, they don't say horizontal distance, that's your hypotenuse. If they ever talk about the length of a diagonal, this is typically in something that was square or rectangular, which we'll see in one of our examples below, that's going to be your hypotenuse. All right, so if we go look at example 4, it's asking us to draw a picture to represent the situation. So of course we're going to be drawing a right triangle, and then to write an equation and solve. We're rounding to the nearest tenth because it's a word problem. We're of course including units. So on the first problem, it says you have a 16-foot ladder resting against the side of a house. Now, we could be very artistic about this, and I encourage you to maybe be a little bit artistic sometimes so you can reason out what's happening. So if we draw ourselves a house, and we talk about a ladder resting against the side of a house, so here's the ground, here's the ladder. This is what it would look like. So we're not saying the ladder is attached to the house, we're just saying it's kind of resting against the side of the house. We have a right triangle happening. I'm going to highlight it in red here. This is the right triangle they're talking about. One of the side of the house, we have the ladder, and we have the ground. So it says the ladder is 16 feet. So remember up above, I said the ladder is always the hypotenuse. So the ladder should be this hypotenuse right here that is in red. So that should be your 16 feet. The base of the ladder is 4 feet away from the base of the house. So that's that distance from base, that kind of wording. That should be your horizontal leg. So 4 feet should be on your horizontal leg. And it says how high above the ground? Heights are your vertical leg. That's the thing we don't know. So we're going to put an X on that. So that's what your triangle should look like. You have a right triangle because the side of the house is meeting the ground at a right angle. You know the hypotenuse, you know the horizontal leg, you just don't know the vertical leg. So if we apply the Pythagorean theorem correctly, we would go leg squared plus leg squared. So x squared plus 4 squared equals hypotenuse squared, which is 16 squared. That would be x squared plus 16 equals 256. If you subtract 16 from both sides, you would have x squared equals 240. If you square root both sides, and notice we're not going to do what we did up above. We're not going to try to reduce this radical. We're going to go to the nearest tenth like the directions say. These numbers get kind of big, so we let you just round to the nearest tenth in your calculator. So if you took the square root of 240 in your calculator and rounded to the nearest tenth, it'd be about 15.5. Because it's a word problem, I do want those units. So the units were feet, so we're going to include the units on the answer. So x is 15.5 feet. All right, let's look at example B. This is what I call a directional problem. You're traveling north, south, east, and west. Anytime I give you a problem that involves directions, I always give you what we call the compass rose. So the north, south, east, and west will be labeled off to the side for you. So first let's read this. John leaves school to go home. He walks 6 blocks north, then 8 blocks west. How far is John from school? So I always say just put your pencil somewhere, give yourself a starting point, give yourself a dot to start. He's leaving school, right? That's what the word problem says. He's leaving school. What does he do when he leaves school? He walks 6 blocks north. Come look over here at your compass rose. North is up, right? So he's going up 6 blocks. And then he's heading 8 blocks west. West is to the right. So after he goes 6 blocks north, he goes 6 blocks west. 8 blocks west. So he traveled from school, and then he went home eventually. He landed at home. But he did that by going 6 blocks north and 8 blocks west. And the question is, how far is he from school? That basically, when they say how far, that means what is his distance? What is his distance from school? So if I asked you how far he traveled, you'd say he traveled 14 blocks, but he didn't end up 14 blocks from school. If you are calculating the distance from home to school, it'd be that direct straight line from the home to the school. And so that would be, again, a right triangle problem where we can apply the Pythagorean theorem. So our hypotenuse is x. So we're going to say x squared. Our legs are 8 and 6, so equal 8 squared plus 6 squared. X squared equals 64 plus 36. X squared equals 100 if you add up those two numbers. If you square root both sides, you end up with an x of 10. You should include units. Everything is being measured in blocks, so your final answer should also be in blocks. So again, kind of just put your pencil at a starting point and do what the words tell you. Go north, then go west, which means you're going up, then you're going left, and complete it with a triangle. Draw a hypotenuse in. That's anytime you have directions involved in the word problem. All right, the last kind of word problem I want to show you is when it deals with something that isn't triangular to start out with. So a television set is definitely not a triangle. A television set is a rectangle. So it says a television set is measured by the diagonal length. A diagonal means you're going from opposite corner to opposite corner. So if I go from opposite corner to opposite corner, it would look something like that. It says a 72-inch TV set has a diagonal that measures 72. So on that diagonal, I just drew in, I'm going to put 72 inches. It says the height of the screen is 35.4. Again, go back up to the top and look at those words that I gave you. Height's always on the vertical leg. So on the leg that's vertical, I'm going to put 35.4. And this is, again, in inches. The question is, how wide is the screen? So the width, we're going to call the missing piece of the right triangle. So again, this is all about right triangles. We are just going to focus in on this right triangle that I highlighted in yellow, because then we can use the Pythagorean theorem. So even though a television set is rectangular, once you throw in the diagonal, you chop it into two right triangles. And we're going to do the Pythagorean theorem on the one that I just highlighted in yellow. So my legs are the 35.4 and the x. Again, my hypotenuse is across from the 90, and the other two sides are the legs. So the correct way to write to use the Pythagorean theorem is to say x squared plus 35.4 squared equals 72 squared. If we square 35.4, we end up getting 1,253.16. If we square 72, we get 5,184. If we subtract 1,253.16 from 5,184, again, very happy we have a calculator, right? We'll get 3,930.84. At this point, we square root both sides, mainly doing that so we can unsquare that x, but must do the same thing to both sides of an equation. If we square root that number and round to the nearest tenth, we'll get 62.7. Our units are our units are inches, so we'll put inches on our answer. So those are the three kinds of word problems you typically see. Something with a ladder or a string or a wire, or something that talks about different directions that you might travel, or something that started out rectangular, but they threw in the diagonal and created some right triangles. Always reference that triangle up above where we talked about where the labels should go. And that is